Today, we welcome ZQ Lee, one of the authors of the NaturalBench paper, which has been accepted into NeuroIPS 2024. This paper challenges how we evaluate the effectiveness of vision language models. VLMs combine the power of visual and linguistic understanding and have shown impressive results on a wide range of tasks like visual question answering. However, this paper raises a critical question. Are these models as capable as the current benchmarks suggest? As we'll learn in this talk, the authors provide some compelling evidence that even state-of-the-art VLMs can struggle with seemingly simple questions about natural images. And this reveals a huge gap between their perceived and actual capabilities. The paper introduces NaturalBench, which is a new benchmark that's designed to address the limitations of existing VQA evaluations. NaturalBench uses a unique approach that forces models to rely on visual input, and this ensures a more accurate assessment of their true ability to understand what is in an image. As we'll learn in this talk, this new benchmark exposes biases in existing models, and it also shed light on the need for further research in developing more robust and reliable vision language models. I hope you're ready for a cool discussion and an insightful discussion on the future of VLM evaluations. ZQ, thank you so much for being here. Go ahead and take it away. I'm excited to get into your paper.
Yes, thank you for the introduction, and thank you for inviting me. Let's get right into it. Today, I'll be presenting our paper that's accepted to NeurlPS 24. It's a new vision-centric VQA benchmark, and a lot of it are talking about how do you weight benchmark biases, existing vision language evaluation. Here's a little bit of context. So when we look into a lot of the recent benchmark for evaluating the advanced vision language model, such as GPT-4o. So for example, here I'm showing an example from the MMU benchmark. I think is a really popular one, essentially testing whether those models are able to understand college level subject. But if we look into these benchmark closely, we'll notice a really significant design flaw, which is that a lot of the questions, you don't even need to look at the image to answer it. And in fact, if we ask a blind language model, such as ChatGPT, to solve these benchmark, they can actually get a performance that's way above random chance. Okay, so I do have a few works talking about these benchmark biases, but for today, I'll be focusing on our newest paper that actually address these issues. Okay, so how do we fix those benchmark biases? Maybe as a bit more motivation, so let's look into more of the recent benchmark. So here I'm taking a bunch of examples from the popular benchmark people now they are using to evaluate GPT-4o, Q12, Llama 3.5, and Momo. So for example, there's the Science QA benchmark, and the question is literally, what's the capital of Massachusetts? And most of us, being US, we know this is Boston. Another example is from the bench is asking if African elephant is the smallest or largest land animal on the world. And it's kind of like a stupid question, like we know is the largest. If we have the knowledge of Wikipedia, we don't really need to look at this image to answer. And here are a bunch more examples that we take from current benchmark. And here's some qualitative study. If we ask this question to, I guess, a blind GPT 3.5, not even the GPT-4, these question can also be easily solved. One of the insight that we learned is if you structure your visual question answering benchmark to have those independent or single image question pairs, you inevitably make your benchmark point to the blind shortcut. Yeah, and here's some quantitative evaluation. We actually try on those benchmark a blind ChatGPT, and it shows that a blind language model can actually surpass a reasonably good vision language model, which in this case is the Llama 1.5. So our solution is simple. We essentially just pairs, so instead of using single image question pairs, we pairs two images with two questions and make sure that these two have opposite answers. So this, I guess, benchmarking protocol ensures that if you have a blind language models that just choose blindly regardless of the image, then you're guaranteed to get a random chance performance on our benchmark. And we're not actually the first one to come up with the solution. This has already been done almost 10 years ago in 2016 by the VQA V2 benchmark. So the paper literally, the title is Making the Vision in VQA Matter. What they're doing is pretty much the same. They're also pairing each question with two images and make sure they have different answers. But when they are collecting this data sets, back then they don't really have like foundation models. So all they're doing is asking Amazon MTurk or like human annotators, like for each questions, find those two images that results in two different answers. So the entire data curation process is really time consuming. So what we do is essentially we take like an existing image text dataset or like image caption datasets, and we try to find those pairs of samples automatically. So here's, I guess, more detailed look. So the step one, given the image caption dataset, we use foundation models such as CLIP, which can essentially like assign a similarity score between any two image text samples. We use it to like basically find pairs of image text samples that are really confusing to CLIP. So here's one example. In this case, so these are the image and text samples in the Flinker datasets. But CLIP actually assigned a higher score for the second image with the first caption. So CLIP makes a mistake here. So essentially, find all the pairs that CLIP is making a mistake. And this will guarantee that we find like images that are really similar to each other's. And once we have those similar looking images with their corresponding captions, what we do is we send the two captions to ChatGPT and asking it to generate two questions that will lead to different answers for the two images. And as the last step, for quality control, we do have human annotators to look at all the samples we collected. We essentially just ask them to solve our benchmark, and we filter out all the samples that human annotators cannot solve. So what that results in is a benchmark that is really simple for humans. So here's one example. We're essentially asking like a simple question about natural images, like is only one view of the motorcycle touching the ground? And the answer is yes for the first one, it's no for the second one. Whereas most of the popular benchmark people are using nowadays, they're testing really complex subjects like art and design, music, biology, medicine. I think as a PhD student in computer science, I'm not able to solve those VK benchmark. Here's a really clear contrast. Like our benchmark is really easy for humans. Even our questions are simple to humans, it turns out to significantly challenges most of the existing models, including the top performing ones like GPT-4o, QN2, Llama 3.5, and Momo. Here's some more quantitative evaluation. So first of all, because each of our testing data point have essentially 4 questions. So we introduce a stringent metric to kind of penalize the blind language models. So we award 1 point only if all the 4 questions are answered correctly. So because of blind language models, they will always choose the same answer regardless of the image. So what that means is that blind language models will guarantee to get a 0 performance on our benchmark. But importantly, when we're comparing human performance, which is 91.4% our benchmark, and also GPT-4o performance, we can see that even GPT-4o is falling short of human performance by around 50%. And we don't just evaluate GPT-4, we evaluate 53 popular vision language models. Don't read the table. The conclusion is most of the models are just 10 to 20% above random chance performance. And all the models are 50 to 70% lower than human performance. Maybe the promising signal we're seeing is if you're using the more recent and larger models, you do get like marginally better performance. It seems like scaling up does help a little bit on our benchmark. So we also try to investigate why our benchmark is so hard. First of all, it turns out like even though the questions are simple, solving each of them can actually require a composition of skills related to object recognition, attribute bindings, relational understanding, and some complex reasoning like logic and word knowledge. So towards this end, we actually tag each of the questionnaire benchmarks with its associated skills for a fine-grained evaluation. And I guess another reason why NaturalBench is hard, this one's really interesting. So if we look at this example and we look at the performance of the models, we can see that apart from GPT-4o, the rest of the models, they're all wrong on this data point because they answer yes to all the questions, even though 2 of them should be answered no. And this is a really common pitfall, like a lot of the vision language model will have. Turns out they are like just really biased towards certain answer choices. And in the paper, we also show that if we just somehow fix this bias to make sure that, oh, your model answered 2 yes and 2 no for these 4 questions, then we're able to see like a double to triple performance. So I think this kind of suggests that, okay, vision language model right now are kind of really biased. And this might account for like why like they often make like hallucinations. And another perspective is our natural bench can actually be used as a useful benchmark to test these models, test like debiasing techniques for these models to make sure that they're more robust for downstream tasks. The takeaway for this work is it's really important to balance your vision language benchmark as well as your models. That's it.
Awesome. Thank you. Appreciate you giving a rundown of the paper. Before I jump into my questions, I want to see if perhaps Jacob has any questions for you here.
Yeah, I really love this work. It's incredibly cool, and it's as many of the most powerful ideas are, incredibly simple and yet incredibly effective at diagnosing these biases. So, what I'm interested in is what was the most surprising takeaway that you had from this entire project?
So you mean the takeaway from the entire
Yeah,
project?
yeah. What was
Oh
the
yeah,
most
so I
surprising
think
takeaway, insight, whatever you want to call it?
yeah. So I guess, first of all, we can see that if you don't carefully balance your benchmark, then your vision language benchmark can be solved using a purely language models. I think maybe that's the biggest takeaway. And that's why we're like revisiting the lessons of like from 10 years ago from the VQ V2 benchmark. So that try to make sure each of your question have 2 images with opposite answers. So that way you need to rely on the model's vision perception abilities to solve the benchmark.
So if one were to take this insight, the conclusion of your project, and try to apply that to make these models, you know, better able to address and understand the visual content as well as the language content, do you think that that would be ideally suited for an additional term or part of the
Yes.
training process, or would it be a fine tuning that you do after the fact, or something else entirely?
Yeah, that's a great question. I think it's related to follow-up work. We are thinking about these questions. And I guess my perspective is, even though for this work, we're mostly focusing on collecting a evaluation benchmark, but I feel like if we understand how to do evaluation or like how to collect the evaluation data set, then I think the same insight can be applied to collect, I guess, a more robust training data set for vision language models. And I guess importantly, our entire benchmark curation process is actually pretty lightweight. Like we mostly rely on like foundation models, and we only apply human annotators for the last step for quality control. So it's really just a one-step check. So I think the same methodology can be applied to collect the training data set in a similar fashions. So that way you'll be getting like pairs of imaging questions that are really similar to each other and are really challenging to the existing models. I'm pretty sure like training on such a challenging data sets will lead to a more robust performance for a downstream task.
Makes sense to me. I love it. I'm excited to see all the follow-up work.
Yes, thank you.
Awesome, ZQ. I got a couple questions here actually about like kind of data set curation. So you mentioned that you have kind of a semi-automated process for collecting the samples for NaturalBench, where you start by identifying these image text pairs that models like Clip or Blip2 fail to match correctly. Can you walk us through an example of how this initial step works? What kind of images and captions did you notice tend to be mismatched by these models, and why might these mismatches be useful for generating challenging VQA samples?
Yeah, so I guess here's one concrete example. So essentially so our data curation methodology first takes like an existing image caption data set. And I guess it can apply in the paper also show that it doesn't apply to just I guess a classic Flinker 30K data set I've been using for so many years. It also applied to some of the more recent and more challenging image caption data sets, such as DASI, which have caption that have even over 200 words. But I guess for a simple illustration, here's an example that we take from Flinker 30K. So essentially, we are taking pairs of image caption examples where a clip score is assigning like a higher score for, I guess, the wrong image caption pairs. What that means is essentially like all the pairs that we're collecting, they will be like really confusable to each other. So like the images will look alike, the caption will look alike. Importantly, there will be some semantic differences in those samples. And so towards that end, we can essentially ask ChatGPT to pick up this difference between the two image and come up with question that will lead to different answers. And
So
I guess in the paper we show that if we don't use like clip to find those like confusable image text pairs, and we just randomly pick any two images, and then the benchmark will be much easier. So it won't be as challenging as it is now.
So two follow-up questions on this. One is, you mentioned you're using ChatGPT as the question generator. You also mentioned when we were looking at one of the examples earlier that ChatGPT or GPT 3.5 was the only like VLM that was able to not say yes for everything. Do you think
Right.
that those two things are related? Do you think that there's some bias in the types of questions that it is
Yeah,
asking?
that's a really harsh question. Yeah, I like that. I think we do got like even my advisor is asking like, okay, so if you're curating your data set using ChatGPT, then maybe this benchmark will also be easier to ChatGPT. Yeah, I think this is like a pretty legit question. Like maybe this is why ChatGPT is outperforming all the rest of the models. But I'll say because we do have like a quality control step, like we do have humans to go through this data set. So at least the questions that we have in our benchmark are the ones that human can easily answer. So no matter if there's a bias, like if those questions happen to be the one that ChatGPT can answer, we believe those are like valuable data points for current vision language model to solve.
The second follow-up, and Harpreet, I'll let you go after this,
Yeah.
was instead of finding natural images, did you consider taking an existing image and then doing some type of image generation or image editing based on that? I think some of the models like OmniGen and MGIE are pretty good at generating things that are semantically distinct, but retain a lot of the other structure in an image.
Yes, so I guess as a matter of fact, I guess I spend more of my time actually working on evaluating those like text to image generator models. I'll say, yeah, I do see like a huge improvement in them, like in generating context images. I think it will be like really exciting follow-up, like to extend, I guess, the same benchmark, but replacing maybe the natural images with synthetic images. Maybe that's the way to go, like for curating the next generation vision language models. I guess right now we focus on natural images because we just feel like natural images are the ones that kind of like lies in the distribution of most of the vision language models. Importantly, even this Flinker image caption dataset that we use to curate this VQ benchmark is already being used by a lot of the open source vision language models. So in other words, like those models already see all of those images. But it turns out they still cannot answer questions that somehow already, those information are already in the training captions. So it seems like all the models, even though they are maybe using those data points, I mean, a lot of models, they don't even release their training data, but I assume they are all using like Flinker is a pretty good training data sets. So it seems like they are still not exploiting the current power of the data sets.
Speaking of using Chat GPT, were there any like specific prompts or instructions that you had to provide to
Yes.
Chat GPT? And did you like do any kind of, I don't know, ablations or anything on those prompts?
Yes, it's a great question. And I guess I don't have the exact prompt that we use. I guess that we have that in the papers, but it's really simple. We just ask ChatGPT to please write two questions about two images. The first question should be yes for image one and no for image two, and vice versa. And we do have like other kinds of prompts for generating not just like binary yes or no question, but also like multiple choice questions that ask model to choose like between choice A or choice B. We find that like just essentially using simple instruction works for ChatGPT.
And you talked about this human verification step. Were there any like specific criteria that you uh, gave to the human annotators to evaluate the questions and answers? And, were there any disagreements between the annotators? How did you handle that?
Yes, these are
Yeah.
all great questions. I really appreciate you must be reading my paper in details. So it's actually simple. So essentially, we just ask human annotators to try this benchmark and try to answer those questions. So like essentially, after we generate all those questions, we send the image and a question to annotator, and annotator should be giving us an answer either yes or no or like A or B. And what we do is we essentially filter out all the questions that human are giving the wrong answers. So that way we guarantee the remaining samples are the one that human can easily solve.
And this must explain why because you have the table 3 there that has like statistics on like the number of mismatched pairs versus number of verified pairs. Does this explain kind of why there was a huge reduction in the number of
Yeah, there's a
samples?
huge reduction. Yeah, I think a lot of it was because Yeah, this is like a crucial insight we probably even didn't talk about in the paper. But essentially, like when we look at, even though Flinker 30K is a reasonably good captioning data set, a lot of time like the caption is missing like important detail, or there are some hallucination in the captions. So if the information in the caption is already like inaccurate, then the question ChatGPT generate will also have the same flaws. So we do unfortunately need to remove those samples. However, when we are using some of the more recent and higher quality data set like DASI, it turns out like we can, I guess, use more of the samples. Like human annotator will be able to do like more of the samples correctly. So even though like our approach is relying on image caption data sets, but like using more recent and higher quality data set does improve the efficiency for collecting this benchmark.
Thank you. You mentioned that the VLMs kind of, you notice that they struggle with questions that involve orientation. I'm wondering, kind of from a practitioner's perspective, somebody who's, might be looking to deploy one of these models for production and, like a real world use case, how could they use NaturalBench to assess whether a particular VLM exhibits this type of bias or, any other type of bias? Maybe what do you think might be some potential consequences of deploying a model with biases like these in real world applications?
Yeah, so I guess maybe the short takeaway is just don't use VLMs for any task that involves spatial reasoning. I think VLM are especially, maybe one example for spatial orientation is like asking, okay, are the two people looking in the same direction? I guess human, we can solve it within a blink. We immediately know, oh, these two person are looking at the same direction, but these two person are not. But turns out vision language model are struggling a lot on these type of questions. So even though like lots of folks are trying to use the vision language model to empower more complex real world application like robotics, I do think like maybe we need to collect more targeted data sets to improve VLM's spatial reasoning capabilities before we put them into the real world.
Awesome. Thank you, ZQ. Jacob, any other follow-up questions here?
That's it for me. This is awesome work. Love what you're doing. Great to meet you and great to have you on the show.
Great to meet you too. Yeah, thanks for all the detailed questions. Appreciate reading my papers.
Yeah, thank you so much for joining us and hope to see you at NeuroIPS. Feel free to swing by our booth, the Voss 51 booth. I'll hook you up with some swag. ZQ,
Definitely.
thank you so much for joining.
Yes. Thank you so much.
Awesome. We'll go ahead and call it a wrap right there, and we'll have this sent out sometime, maybe a week before the actual conference. We'll push it all over social media. Sorry about that. Sorry about that. Cool. Well, thank you very much, and we'll see you. Make sure you come say hi at the conference.
Definitely, I'll do that.
Yeah.
I'll do
Yeah.
that. Yeah, nice to meet you both.
Bye.
Cheers.
Have a good one.